All right, so now that we've proven Hall's theorem, I want to prove another theorem due to Burge. This one is actually the one that gets used for creating algorithms for finding maximum matchings in bipartite graphs, and in graphs in general. So it relies on the following concept. Giving a matching M, a path is called M alternating if every other edge on your path is in the matching. So the reason why we say alternating is because when we draw pictures of these, you start to see they alternate in colors when we use red to represent the edges in the matching and black for the other edges. Now we're going to say such a path is M augmenting if it is M alternating and its two endpoints are unsaturated. Notice here that if they're unsaturated, the corresponding edges on the path both have to be black. But more importantly, that also means that there's not a possible red edge attached to either of them. Because if there was a red edge, then you could actually extend the alternating path to an even larger alternating path. All right, so the theorem is that a matching is M is maximum if and only if G has no M augmenting paths. Or equivalently, if a matching is not maximum, then you must be able to find an augmenting path. And yes, that's the reason why this forms the basis of most algorithms for finding matchings. The algorithms start with an empty set and just start throwing in edges and then start looking for augmenting paths. And then if it can't find any, it concludes that the matching is maximum. Otherwise, it switches. So it's worth pointing out the motivation here, if you look at the picture I drew, is that there are 3 black edges and 2 red edges. And so if I switched so that the black edges were red and the red were black, I now have a matching that's larger. And I'm guaranteed that this can work because the 2 endpoints in the path are not incident to a red edge. However, traditionally, to make things completely formal, we don't use the concept of color in the proof itself. To be very precise, instead of saying switch, we use the phrase symmetric difference. So the symmetric difference of 2 sets is the union of their set differences. In other words, in this case, since we're dealing with edges, these are 2 edge sets. This symmetric difference is the collection of edges that appears in A or B, but not both. So with that definition in mind, let's do the proof. First, suppose M has an augmenting path. Then, if you look at the number of edges on the path that are not in the matching, as depicted previously, it has to be strictly bigger than the number of edges in the matching. And that's because this path has to start and end on a black edge. In particular, when we take the set difference between M and P, we're going to get a new matching that is strictly bigger. So M is not maximum. So if you have an augmenting path, you do not have a maximum matching. And the reason why this set difference is larger is because what we've done is we've taken the path and now we've added the non-matched edges into our new matching and removed the matched edges from P. So we swapped the colors red and black on the path. All right, now to prove the converse direction, let's suppose M is not maximum, and let's let M prime be a maximum matching. And we're going to let G prime be the graph given by taking the set difference of these 2 matchings. So the idea is that you had some red edges, and now you also happen to have blue edges, and you're taking the set difference, which means anything that was in both gets deleted. In particular, every vertex in your graph has to be incident to at most 1 edge of either matching, and so the degree of such a vertex is at most 2. Each vertex can only be incident to at most 1 red edge and 1 blue edge. And so then we start looking at it. What do we know about graphs where every vertex is degree at most 2? Well, if we restrict to the components of the graph, you either get a path or a cycle. And since every other edge of a cycle is in one of the two matchings, we see that the cycle has to have even length. In other words, we can't have an odd length cycle because then you have to end up with a vertex incident to two red edges, and that's not possible because the red edges have to form a matching, or two blue edges. So we now know that every cycle has to have even length, and in particular, the number of edges in the cycle from M and the number of edges in the cycle from M prime have to be the same. By the same logic, if you look at an even length path, the number of edges on the path in each matching has to be the same, because the colors have to alternate between red and blue. So the point is, since there's more edges in M prime than in M, we see that there must be an odd length path. And more importantly, that odd length path has to have more edges in M prime than M. In particular, that means we have to have a picture like this, where blue is M prime, where the path starts and ends on a blue edge. While then, this path Q, if we go back to viewing these blue edges as being black, we now have an alternating path that is M alternating. And we also know that these endpoints can't be incident to red edges because this was a component in G prime. And thus this path is M augmenting. And so what we found was that if your matching is not maximum, you must be able to find an augmenting path.